All right, this is chapter 14, lesson 4. So this is calculating enthalpy changes. This is the second lesson that I've posted today. You will have noticed that there is a chapter 14, lesson 4 worksheet on Teams. So make sure that you bring that guy up and let's go through that together. All right, so what we're going to do is we're going to learn about a process called Hess's Law. Hess's Law is actually a lot of fun because it's kind of like a little puzzle you get to figure out. So hopefully you'll be able to get that done as we go through. We're going to look at the standard enthalpies of formation table, and we're going to look at the basis for that. We're going to look at how the delta H of a reaction, this little RXN, is shorthand for reaction. We're going to look at how to calculate that using thermochemical equations, and we're also going to look at the enthalpy change for a reaction using standard enthalpy of formation data. So there's going to be a lot of calculation in this. So here's your two new vocab, Hess's Law and standard enthalpy of formation, and so we'll get to each one of those individually. Hess's Law is pretty simple. It just states that the total amount of energy lost or gained in a reaction is independent of the number of steps taken to get from beginning to end. This little diagram is actually a really good way to explain it. If I'm at the, third floor here, and I jump off the third floor, I fall to the first floor. However, I can jump off the third floor and land on the second floor, and then bounce off the second floor and hit the first floor. The total energy lost from the third floor to the first floor is the same whether or not I fall there directly from third to one, or if I bounce off the second floor step before landing on the first floor. That's the idea of Hess's Law. If I look at this, I have methane plus oxygen. Well, methane plus oxygen can be converted directly into carbon dioxide and water in one step. And when it does that, it releases negative 890 kilojoules. However, this same reaction can go through a second step first. The methane and the oxygen can be converted into carbon monoxide and water and half an oxygen to then become carbon dioxide and water. So it can actually go through two pathways. Well, in the second step here, it goes here and then to there. So if I have to say, well, that's going to be them added together, if I add all that together, it equals negative 890. So the total amount of energy from going from the top of this to the bottom, or taking a second step, the total amount of energy lost is the same. It is exactly the same regardless of the number of steps taken. That's Hess's Law. Now, Hess's Law is particularly useful when we can't determine the amount of energy released from a chemical reaction. For example, you've seen the burning of magnesium in the lab. When I burnt that magnesium, I said, don't look right at it. It's so bright, it'll hurt your eyes. Well, that reaction releases so much heat so fast and so violently, it's impossible to tell exactly how much heat is released from the burning of that magnesium. That's Mg plus O2 yielding MgO. And so I have to balance that guy. That is a really hard reaction to say, well, how much enthalpy, change in energy, how much enthalpy is released? Well, that's a good question. However, even though I can't determine exactly how much energy is released from that reaction because it's too fast, it's too violent, and it produces several different magnesium products with the nitrogen in the air, it's a really, really complex thing to try to figure out. We can actually figure it out using Hess's Law. So in your book, if you look through the example they have in your book, it's the exact same idea, but instead of talking about magnesium, they talk about the burning of sulfur. So the burning of sulfur, again, releases a lot of heat. It's difficult to capture all that heat, and it gives us this reaction here. 2 sulfurs plus 3 oxygens yield 2 sulfur trioxides. So since we can't synthesize this directly, we can use Hess's law like this. So we can say this is the reaction we're looking for, but we know that there are 2-step reactions that take place. Okay, and so basically we set this up like a little math problem. So if you ignore the equation on the top and just look at these two here, we're going to take equations A and B, and we're going to turn them into the last equation, which is what we're looking for. Okay, so we're taking 2 known values and we're going to try to come up with an unknown value. So here's how we do this. I've got 3 steps here to solving a Hess's law problem. Step 1 is make sure your reactants are reactants and your products are products. Okay, so here's how this works. I have sulfur as a reactant. Remember, this is the equation I'm trying to solve for. Well, sulfur's a reactant here, and it's a reactant there, so check. Oxygen is a reactant here, and oxygen is also a reactant there, check. Sulfur trioxide is a product, but sulfur trioxide is a reactant here, so that doesn't work. So 2 of them work and 1 does not, which means I need to take this equation and I need to flip it to make sure that sulfur trioxide is a product, because the one that I want in the equation that I want, sulfur trioxide is a product. So I'm just going to flip this equation. I'm going to take 2SO2 plus O2, and I'm going to say that yields 2 SO3s, and I'm going to say the delta H is equal to negative 198 kilojoules. And so I'm just going to cross out that whole equation. Now, if I flip an equation, I have to flip the amount of energy, because if it required 198 kilojoules for that equation to run forward, then it will produce 198 kilojoules when that equation runs backwards. So if I flip the equation, I have to flip the sign. So be sure to flip the sign on the enthalpy. So now let's look. Sulfur is a reactant, it's a reactant. Oxygen's a reactant, it's a reactant. SO3 is a product, SO3 is a product. Step 1 is done. All right. Now I need to adjust the molar amounts to match the final equation. There are 2 sulfurs here, and up here there's only 1 sulfur. So I need to double the amount of sulfurs. Well, if I double the amount of sulfurs, it's going to double the amount of oxygen, it's going to double the amount of SO2 produced, and it's going to double the amount of energy produced. So I have to multiply that by 2. I have 3 oxygens here. If I look, I have 2 oxygens here, and 1 down here makes 3, so I'm good. And then I have 2 SO3s, and there's 2 SO3s, so I'm good there. The last step here is to cancel. Now, anything that is on the opposite sides of the arrows can cancel from one another. So if I look here, I can cancel 2 SO2s and 2 SO2s. They're on opposite sides of the arrows, which means they cancel out. Now, I like to cancel things out and then make sure if what I'm looking for in the final equation is what I'm left with. So I have 2 sulfurs, 3 oxygens, and 2 SO3s, 2 SO3s. So now that I know that I've got everything where I want it, the last thing we have to do is add up the enthalpies. So I have negative 297 times 2 minus 198. So when I carry that out, I have negative 297 times 2, which is negative 594 minus 198, or plus a negative 198. Basically, I'm adding all this up, and that's going to equal negative 792. So the delta H for this is negative 792. kilojoules. All right, so let's just review. There's a lot of stuff on here. Basically what I did is I took my final equation, the one I was looking for. This is the equation I'm looking for, and I made the top two equations match it. So I had to flip the bottom equation, which caused me to flip the sign here, and then I had to multiply the top equation by 2, which is why I multiplied by 2 here. Once everything cancels and it's the way we want it, then basically we're just adding the enthalpies together. So we had to multiply the top one by 2, and then we add the negative 198, which gives us our answer. So this is the same thing in graphical form. We went from the top to the bottom. This was the one we found out. They got negative 792, and we got negative 792. They found the first step from top to almost to the bottom is negative 594. Negative 594. And then from the bottom, from the second step all the way to the last step, they got negative 198, which is also what we got. So basically we're just adding these two together to equal this one. All right, so let's try another. If you want to pause the video and try this one, I'm going to work this one out in just a second. If not, then you can watch me work it. I like to flip things around just a little bit. I like the final equation to be on the bottom, almost like it's the answer to an addition problem. So I'm going to take 2H2 plus O2 yields 2H2O with a delta H of negative 572. I like to leave space just in case I have to flip. I can have room to write. So I have H2 plus O2 yields H2O2 with a delta H of negative 188. And then I'm going to draw a line, and then I'm going to say 2H2O2 yields 2H2O plus O2, and I want to know what is the delta H of that guy. Well, I first have to make my reactants reactants and my products products. So my only reactant is H2O2, and it's a product over here. So I need to flip this equation. H2O2 yields H2 plus O2 with a delta H of positive 188. And then I'm going to cancel out or cross out that reaction. Now I'm going to look at my H2O and my O2. I have H2O is a product and H2O is a product here, so I'm good. O2 is a product and O2 is a product here, so I'm good. All right, next I look at values. I have 2 H2O2. Well, I only have 1 in this equation, so I got to multiply the whole thing times 2. So I got that. Now I look at my 2H2O. I have 2H2O, I'm good. And then 1O2, I have 2O2, but it'll take care of itself here in a second. Now what we're going to do is cancel out anything that's on either side of the yield sign. So I have, the only thing I have is 2H2 and 2H2. They cancel. And then I have 2O2 down here and 1O2 up here, which means I can cancel that O2 with just one of these O2s. So instead of it being 2O2, I'm just going to get rid of that and say it's 1O2 because I canceled one right there. All right, so now that I've canceled that, I'm going to make sure that I've got everything I want. I have 2H2O2 is going to yield 2H2 plus O2, and that's everything I'm looking for. So now I just have to add all this together. So I have negative 572 plus 188 times 2. So when I solve that, negative 572 plus 376, I get negative 196 kilojoules as my answer. All right, so that's how you solve a Hess's Law problem. So now you can do numbers 1 and 2 on your own on the worksheet. So go ahead and pause the video and do that now. All right, standard enthalpy of formation. So a standard enthalpy of formation is defined as the change in enthalpy that accompanies the formation of 1 mole of a compound in its standard state from its elements in their standard states. So I could take anything. I could take like C6H12O6 and say, what's the enthalpy of formation of this guy? Well, I would need its elements, carbon plus H2 plus O2, like that. And I would say, well, I need 6 carbons and 6 hydrogens, because 6 times 2 is 12, and 3 oxygens. So this would be the equation for the enthalpy of formation of glucose, and I would say that delta H sub F is equal to, and I'd have to look that up. I don't know what it is. It's a reference. So standard enthalpies of formation are always given in a table, but if you're given any compound, you can figure out its standard enthalpy of formation by just taking its elements, and I say in their standard states, hydrogen always exists as H2 and oxygen always exists as O2, and that's the elements that form it. And when you have the elements that form it and you balance it all out, that's the equation for the standard enthalpy of formation. So we have sulfur trioxide here. So I have 1 sulfur plus 3 halves of an O2, which would give me 3 O's. And so that gives me the amount of sulfur and oxygen I need to make SO3. And I can see its enthalpy of formation is negative 396. You look it up. These are values that are found in tables. You can type in a table on a Google search, enthalpy of formation, and it'll give you this huge table of just about every known compound and its enthalpy of formation. Now, one thing to know is the enthalpy of formation of an element is always 0. So elements have an enthalpy of formation of 0 because an enthalpy of formation is the amount of energy required for a compound to form from its elements. Well, an element would just form from its own element, so it's a 0 total change in energy because however much energy it took is the same amount of energy it released when it formed, because it didn't actually form anything. It just stayed the same because oxygen now is oxygen later. So the enthalpy of formation of an element is 0. Standard enthalpy of formation can be used with Hess's law. For example, sulfur hexafluoride is formed according to the following equation. I have H2S plus 4F2 yields 2HF plus SF6. And it says, what's the enthalpy of the reaction? Well, you can set up the step equations by using the table below. So I can say my final equation is going to be H2S plus 4F2 yields 2HF plus SF6. And so I can actually set up the other equations. I can say H2 plus S yields H2S. I can say 1/2 of H2 plus 1/2 of F2 yields HF. I can say S plus 3/2 of an O2 yield SO3, and S plus 3F yields SF6, 3F2. So I've got my 4-step equation, so now I can start flipping them. I'd need to flip this guy, and I would write out this is negative 21 kilojoules, 273 kilojoules, negative 393, and negative 1220. So I would I'd flip the first one because this is a reactant and this is a product, so I'd have to flip that equation, which means this would flip. I have 4F2. Well, down here I have 3F2 plus 1/2 an F2, that makes 4. and then I have 2HF. I'd have to multiply this whole thing by 2, which means I'd have to multiply that guy by 2, and then SF6. And so now I've got all that, and I can add all this up together. So that's just real fast, just to show you that you can use all these enthalpies of formation as Hess's law. But there's an easier way. There's a much, much easier way. All right. So here's the same reaction, and when you solve through it, you'll get the same answer I got. All right. An easier way to do this is what's called the summation equation. The summation equation just says that the delta H for any reaction is equal to the delta HFs of the products minus the delta HFs of the reactants. Now they have these sigmas here, which just means the sum of the delta H of formations of the products minus the delta H's of formations of the reactants. So here's the same equation, and instead of solving it in terms of Hess's law, we can actually solve this in terms of summation. So here's how it works. If we take, and this is it solved here, but I'm gonna do it again so you can see what we're doing. I'm gonna take H2S plus 4F2 yields 2HF plus SF6. And I think when you see this, you're going to be like, oh yeah, that's way easier than trying to do it Hess's law. What I like to do is just put the value, the enthalpies of formation for each thing just above it. So H2S, its enthalpy of formation is -21. The enthalpy of formation of fluorine, which is an element, is 0. Remember that the enthalpy of formation of an element is just 0. HF, its enthalpy of formation is -273, and SF6 is -1220. All right, so now I've got my enthalpies of formation on my equation. So now all I'm going to do is multiply them by their number of moles. So the number of moles here, so this is -21. 4 times 0 is still 0. 2 times -273 is going to be -546, and 1 times -1200 is 1220 is 1220. All right, so now I've got my reactants and my products. I'm going to add them together. So -21 plus 0 is -21. -546 plus -1220 is -1766. Now, remember, delta H is equal to the delta H of the products minus the delta H of the reactants. So it's -1766 minus -21. So -1766 minus -21. That's going to give me -1745. And that is my answer. And that's the same thing they got there. So that's using the summation equation. Summation just means the sum of. Okay, so hopefully you guys can see how that worked. So let's try one here. If you want to pause the video and try this, I'm going to solve through it in just a second. And then you can do a few on your own. So if you've not paused the video, then let's do this together. So we have CH4 plus 2O2 yields CO2 plus 2H2O. The enthalpy of formation of CH4 is -75. O2 is an element in its standard state, so it's 0. Carbon dioxide is -394, and water is -286. So this remains -75 plus 0. I have -394 plus 2 times -286. So I have -572. This side remains -75. negative 394 plus negative 572 gives me negative 966. Delta H is equal to the delta H of the products minus the delta H of the reactants. So I have negative 966 minus negative 75 equals, and that gives me negative 891 kilojoules, and that is my answer. All right, so that's how you do the summation equation. It's pretty straightforward. Hopefully you can get numbers 3 and 4. So that concludes this lesson. So do numbers 3 and 4 on the worksheet and submit that. If you have any issues, I'll be holding office hours tomorrow at 10 a.m. and I hope everybody's still doing great.